Welcome back to COG 266, Brains, Minds, and Consciousness. Today we're going to keep going into the mind, into one of the most abstract, interesting, and often controversial topics of how does the mind represent things? Representation. It's this concept of how we can take something from the world, as we've discussed, and make it usable internally somehow. Something in our neural patterns that stands in for something in the world. So first, what is a representation? In a lot of ways, it's a model or a map, for example. It can be a way to represent the world. So just in a basic sense, not even within the brain, this is a map of an island, right? But it's not the things on it's not the island, right? It's not the same thing as the island. It is a map of the island. It is a representation of the island. There's all kinds of information available here that we could use to make sense of the world around us were we on this island. We see that there are stone piles in the north. We see that there is a well to the west of the little tree oasis there. Looks like there's a beach to the southeast. These are all things, symbols, that stand in for the real world experience of the countless grains of sand, huge piles of stone, all that we've scribbled down on a little piece of paper and then printed onto this screen for you. That is a representation, a reduced form. So, that concept put out there, we've seen a lot of how we can start to associate ideas, right? Take basic stimuli and combine them into a little bit more complex response patterns. So, mainly, being able to predict the environment and plan your behavior around it leads to things like our daily routines. It's a more complex structure, but it's built from all these little basic things that we can do, like predict what's going to happen when I step outside. So here's an interesting one. And starting us off with a question here. Goats could travel about 25 kilometers to get food they need before returning home every day. That's kind of like we do. We'll run our errands, we'll go and, you might go to multiple classes, whatever. When it's time to go home, what do? Do you just retrace your exact steps? Or do you take the shortcut on your way home? The exact steps is what we have experience with, but the shortcut implies we have some internal understanding of what direction I should go that's not just backward, not just something I just saw, It's not about memory of today, it's about knowledge of the space, right? We do that, and goats do that. We're not the only ones that have this capability. So shortcuts, the interesting thing is that you don't have to know a place. You don't have to know a campus for thousands of hours to figure out that there are shortcuts, right? Even in environments that we've barely inhabited at all, we can use our knowledge of the space that we build in more or less real time to plan a novel route that gets us home faster. But the question is, when you're looking at this from the standpoint of the novelty of the brain, right? That's kind of, we've been growing from the raw inputs and outputs up to this more abstract stuff. How do we achieve that? How are we able to build that representation, that representative understanding of the world around us? Because just looking at things that are in the environment and things that we've experienced directly, it's not really enough to infer something new. This is where the idea of cognitive maps comes in. So we can use structured representations of the environment, storing different locations and their relative locations, right? So this thing is to the left of this, and this thing is further to the right of that. And all the properties and events and stimuli, everything that we experience in the world and see happen in the world helps us start to structure this internal map. So these maps they are useful internal models, right? Models, representations, reduced forms of the outside world that help us make predictions. Again, that's the whole point. If basic classical conditioning type scenarios help us make predictions using the actual world stimuli, and cognitive maps help us make predictions using an internal, we hang on to this internal form that we're able to reuse. Now, let's look at an experiment that really kind of shows how this works. Tolman, 1946. Tolman trained rats to run this very simple maze with a long, winding path here, right? Rat goes in, there's a little foyer kind of type circle area, and then they run up this area here, this little, presuming it's a ramp, and then they got to make a couple of turns, and then they find the food. Yay! Now, Tolman then, so they train the rat to do this, right? Run this little maze every day, run this little maze every day. Now block the path and present a whole array of options of where to go next. The question is, where did the rats choose to go, right? They had their one option that they actually had direct experience with vanished. It was shut. And then a whole bunch of other options opened up. Where did the rat decide to go most times? They almost always went right for the food. That's awesome. That means that the rats have picked up some kind of relational information about the relative locations of the path, of lots of things here. The paths themselves, the turns that they made during that previous path, and also the distances, right? And the food. They didn't get lost and turned around. They didn't get confused about, I had to turn right and then left twice. I'm not sure how far I am. They really did internalize all these distances, angles, not in the, I know how to do the math sense, but in the idea that they were able to build a pretty good map. So it's not just a chain of very simple stimuli like, this door means food. Yay, I'll go to that door, right? They are doing something more complex. And if a rat is doing something this complex, imagine what we are doing, right? Literally now as you listen to this. So, representations. Minds could be described as representational entities. This may be the best sort of shorthand way to talk about a mind. We've talked about a few different definitions here, but we already know they're abstract, and the idea is that a mind really functions at the level of this representation. Everything the mind does operates on copies of things from the real world that we're calling representations. And these copies are reduced forms that are operable in the functions of the mind, right? So it's not the raw pattern of light that the mind is interested in. It's what that light signifies. What does it mean about the outside world? Is there a tree or is there a person? I need to know the difference between those two things. So, lots of representations available. Objects, we understand the apple. Properties of things. The apple is large. That's a property, right? You'll see that language is very helpful here. Other concepts, the apple exists. It's not an inextant apple. It is an extant apple. Desires, I would like to eat the apple. That's something that we can internalize. That's something that we can hold on to in our representational space. Emotions, I'm sad that the apple is out of reach. Nations, this apple breed originated in Japan. Cool. Colors, I can tell this apple is red and green. Molecules, this apple is made mostly of carbon. All of these are representations that we use to understand the world. Now let's try something. Remembering, was there a tree on the map that we saw earlier? Give yourself a second, a couple beats. I bet it'll come quickly or not at all. So, yes, there was. Can you remember where it was? If you pulled from memory that it was kind of in the middle near the little pond or lake or whatever, you're right. Now, if I leave the tree to travel to the rocks, do I pass by the red tent? Again, give you a second. It is not visible, but you've seen it, and you remember things about it. But the question is, are you remembering just a bunch of things that were pertaining to exact things that you dealt with? Or can you take this new sort of... There was lots of information there that you didn't really care about before, and now you do. Can you extract it? The answer is no, because the rocks are to the north and the tent is to the south. But if I travel from the rocks to the beach, do I pass by the flowers? Again, constructing these more complex, this representation of the map itself, which is itself a representation of the world, but also within the representation of the map, these paths that you're trying to summon up and build to be able to answer these questions. The answer is yes. You do pass by the flowers. Although, sorry, those flowers might be a little blurry. The things on the right, little purple critters. So, how did we represent this? Representing the island. What mental representations are involved when you answered these spatial questions when the map is not present? So this gets at the question of what parts of the world do we actually need to store? We're clearly not storing every single thing. I could probably ask you a dozen questions about the last time you went out for a walk. Hey, how many squirrels did you see, right? You won't know unless, you probably noticed one, but what about the 25 others that came into your vision? Another question, though, is that do we actually need a spatial representation? Or can we just do the whole thing in relationships, right? The tree is moderately northish of the red tent versus having a more robust kind of whole internal picture of the map. So this is the sort of the swirling question of representations. What mental representations would you need to be able to text a friend? Something, right? You gotta kind of remember how to interact with your phone. You'd need some words that you're going to actually say to them, right? But what about to ride a bike? That's a very different experience, right? And it's almost automatic after a certain point. Are you relying on representations there, or does your body just kind of know it? So, let's keep digging. What are representations? The most basic way to think of them is that they are symbols. Much like language, much like anything that you encounter, like semiotics, right? The symbols of the world. They are symbols that stand for something else. That map was all symbols that stand for something else. Peirce, in 1902, gives these three interacting components that are at play when you are dealing with a representation. There is the object, what is being represented in the world. There is the symbol, the representation itself, and then the interpretant, the meaning or content of the symbol that gets us there. So in the world, there could be a tree. There is certainly the symbol, the word tree, and then the interpretant is all the things that we can extract from this representation, such as we know that trees are more or less tall, taller than us at least. We know that they are plants. We know that they are woody. So the idea is that you can then use the symbol for other information, for other operations, even though the world is irrespective of this. The tree exists whether the symbol does or not. We can interact with both. We can build more interpretations from the object or from the symbol itself that we already have. So Representations, the idea is that they are containers for meaningful information from the outside world. They can be literal symbols like words, signs, and symbols, or they can be like kind of less symbolic, meaningful relationships. Fire leads to smoke, right? Or I guess smoke can lead to fire if you're a Boy Scout and you learn how to do all this stuff. They are related, right? So being able to map two symbols that are not connected together in a new sort of relational concept. Symbols, or representations rather, can also be abstract. So abstraction is sort of the core thing here. And I talked about this at the end of the brain segment as well. Symbols, that as things get more abstracted, they get more representational. So they don't need to have anything explicitly in common with the original object, right? The only thing that matters is that they are consistent. As long as the abstract symbol represents the same concept, it doesn't matter what it looks like. So, for example, the number 9, it doesn't look... We look at that number 9 in the upper left there in the English Romanized numerical system. And it's just a squiggly boy. It's a hook. It's a weird... Looks like a fish hook. Why does that mean 9 objects? 1, 2, 3, 4, 5, 6, 7, 8, 9. Every language has their own way of representing the quantity of 9. And we all use them consistently, even though they are meaninglessly connected to the concept itself. Here's an apple. I can say the word apple, and you know what I'm getting at. I can show you a little representation of an apple. You know what I'm getting at. I can show you a corporate logo, and you still know what I'm getting at, although it has a little bit different connotations. These are different ways of capturing the world in these reduced forms. Now, one of the big questions is, why should we represent at all? In some philosophies, it helps with this mind-body divide, right? So if you believe in a strong division between mind and body, it helps you understand how, well, the body just makes a sort of leap of abstraction, and then the mind takes over from there. We toss the representation up to the mind's space, and it does its mind stuff up there. But less in the philosophical end and more in the just the pragmatic end. We're organisms, right? And we need to be able to make useful informed decisions about what's happening in the world around us. The problem is that the world is vast and complex, right? It's extended in both time and space. We are dealing with a world that is way bigger than us and has infinite detail. You know, you look at the apple, you know it has skin, and you know it has cells. I can't quite see those, but I know they're there. All the way down to atoms and quarks and leptons and such. So the world is super complex and vast and huge. Our minds are also super complex, but they only have so much intake, right? The senses are limited, and capacity too. We can't store literally everything all the time, even though our brain, there's questions about, quote, how much data does our brain store? There's lots of ways to frame that question. We'll leave that on the table. The point is, though, that you can't store everything. You're one biological entity, right? So your neurons can only get so tuned, and your storage is only so big. Your traces are only so they're fallible, right? Your memory can fail. We already know that. So what we need is some way to operate on ideas that are meaningful in the outside world, but without having to capture the whole dang thing. So, for example, a tree. A tree is actually, if you think about it deeply, it's nearly infinitely complex. It's made of wood, but how does wood work? What are its cells, its chemistry, its atoms? What does wood need to continue to grow? How is wood grown? Is it growing currently? All the wood is there. Is there bark? How does bark work? How do sugars work? Further up, it has leaves. Leaves are completely different than wood. What's going on with chlorophyll? How does this thing live? How does it interact with its ecosystem? Where do its roots go and interact with? How do the animals that live in it help and hinder it? And again, zooming out and zooming in to different levels of chemistry and biology and all the way down to physics and math ultimately. You can analyze a tree for your entire life and you would still learn a lot. But tree is just a symbol. It's a placeholder for us to point at the whole shebang of the kinds of things that we do know about trees. I just said you could spend your entire life studying a tree, right? You would be writing things down, right? You would be forming concepts about the tree. You would be relating the tree to other symbols, ways that it's useful, ways that it's, oh, if I do this, it dies. Oops. These kinds of things about the tree. Those are the kinds of things that your brain and our brains are into in terms of representation. So the symbol for a tree, it's this it's a little piece of memory that allows us to think about trees when we're doing other operations. It doesn't represent everything about a tree or everything about all trees, but it's a starting point for us to be able to wield the concept of tree and all the things that are related to trees in a mental space without having to program every squirrel and atom of a tree. So, here's a broad question. How accurate does a representation need to be useful? Here's a scallop. Scallops don't have much. They are little shelled creatures that live on the ocean floor. They are clammy in a sense, but they're little filter feeders. They just kind of absorb things from the world and sit there and wait, right? What do scallops have? Scallops have many eyes and very few neurons. They don't have a lot of thinking to do being filter feeders. Now, consider the world that the scallop lives in. It's this colorful, super complex, beautiful, they live in reefs, coral reefs. They live in, anywhere that there's lots of vegetation and things going on the sea floor. There's also lots of predators. So, the scallop's, one of its primary maneuvers in this world, in contrasting these two things, the scallop has tons of eyes and very few neurons, and it lives in this complex, colorful, beautiful world with dangerous stuff everywhere. One of its primary behaviors that it needs to be able to survive is detect a change in light, propel yourself away. You may not know this, but scallops can move. This is why they have this clammy shape. They can open and close their shell rapidly to locomote. They'll puff themselves across the seafloor and try to get somewhere where there's not a predator. So here's the question. Do scallops need representation? What would it require to achieve this simple behavior? Does it understand all of the colors and the details in its world? It lives in this beautiful seabed. And the question is, not only does it need to, but is it possible for it to? Can a scallop represent the world, the colorful world of the seabed in its internal system if it's never even had to come close to needing to use that information? In a different vein, bees. Similar. What do bees need to represent their world? They do actually a pretty good job. Bees are a little bit more complex creatures. They understand things like the locations and distances of flowers, the times of day. They need to understand the light implies different things about the way flowers will be accessible. And flight dynamics, they got to fly. And that's not to say that they aren't just sort of internalized and habituated to it, but it's a complex thing to fly around in a world that's windy, right? They have a lot more things that they must respond to and hang on to internally than a scallop needs. Now, does this mean that bees are doing the complex math, physics for flight? No. Are they doing trig to figure out the flower locations? Not necessarily, right? A bee is not necessarily solving a math function to figure out how to communicate how far. Did you know that they can communicate to each other how far something is by doing a wiggle dance? They will wiggle and do a circle, wiggle and do a circle. The number of times they wiggle sort of implies how far-ish in terms of flight patterns. So bees need more, clearly, than scallops do. Scallops don't need much. They don't need much complex pattern matching inside. And this puts things on a complexity gradient, right? Representations really only need to be as complex as required to guide our behavior effectively. Therefore, scallops likely only really need their super simple reflexes and a small amount of conditioned responses. They need the basic stuff that we talked about before. Bees need a little bit more going on, but maybe not to the level of the physics equation. They're not solving trig and physical trajectories in the wind. They are doing something, but it's not that complex. Now, human physicists, on the other hand, who need to work out these problems all the time, they are doing a whole lot more, and they need to represent more things. Now, whether or not humans are capable of representing all of the things needed to do good science, that's a can of worms, said the scientist. So, all to say that the representations will scale with the system that uses them. They will scale with how complex their internal patterns can be. Our brains are great big things that have lots of ways to twist and move, patterns of activation to represent a whole lot of different things in complex ways. Whereas a scallop, it's only got a handful of neurons. It doesn't need to do that, and it probably can't. Its internal life is not as rich. Okay, so more things about representations. They're all going to fall on a spectrum of analog to digital. Any given representation will be on this sort of spectrum. None of them do this, but a fully analog representation of a thing is going to be a literal copy of it, as high fidelity as possible, perfectly resembles the object, all that. Not really useful because that's not really abstraction, that's not really lightening any kind of load, right? But on the other hand, a fully digital representation is just totally arbitrary. It can be anything so long as it signifies the object, ones and zeros. A light being on versus a light being off in the fish example from last time. It's meaningless until the fish ties the information to something else, right? The fact is that most representations are going to fall somewhere in between. You can have a sort of vivid mental image of a tree that you remember from your youth. You can have sort of a idealized concept of a tree, kind of know what shapes it has to it. Or you can have just the letters and the word tree. These are all different representations along this scale. So let's talk temperature. How might we represent temperature? We have cold, warm, and hot, the words, right? We kind of understand those. You can have a sort of visual representation of them. We remember things that are cold. We remember things that would be ice cubes for water, for example. So this is sort of a concrete example. More analog than others, right? So we know that it's warm, and then we remember that boiling water is hot, right? These are different ways that we can access the concept of temperature by remembering water, by remembering vivid examples of water. We can also think of a thermometer, right? A thermometer is something that we can interact with in the actual world. These old mercury ones a little less so these days. Most everything is digital now, but it's still a nice illustrator of lots of information is available. It looks very real. It looks very complete, right? It's an object that you kind of know how to interact with. You can conceptualize cold, warm, and hot along that object's, how full is it? Could also do color. But we're getting a little more abstract here, right? We've left the world of concrete examples, and now we're into sort of things that still make sense. We're used to things that are hot being red hot, and things that are maybe warm being a little less, sorry, red hot being the concept. And then down to cold is something just like, I don't know, fleshy tone, right? So you have this gradient of color that still happens to represent a little bit of the concept of heat. Now, you could keep going and get more and more abstract into squares. Now, these don't really bear any resemblance, but they still represent sort of the concept of the energy, right? The heat energy in the object. Even further, we've got a numerical system of this is the Fahrenheit system or the Celsius system, right? So these are all different representations of these concepts. We have the higher analog stuff on the left. We have the picture. We have a meter. We have color. We have size. They are getting less and less like the thing they're trying to represent. Fahrenheit and Celsius, there's arguable differences between those. Obviously, scientists, we must favor the Celsius, but Fahrenheit has its due. It's a little more human scale for what cold means. Anyway, so another way to think about representation is time. We have analog clocks, we have digital clocks, and we have our old highly analog sundials, right? Those things they are really fascinating because they capture they use all the insane dynamics of the sun and shadow and orientation of the planet and the orbit of the Earth and rotation of the Earth. It's all captured in this little thing. It's very integrated with its world. It is the most analog that we can get in terms of representing time in the physical world. So, things that more resemble the source are analog, while things that don't resemble the source almost at all are digital. And the gradation, we need that because some elements of a representation may resemble the source, while others don't. And this is pretty useful in terms of understanding how complex does your representation need to be to make sense of things. Real quick, if we go back to the temperature, you don't really need, if I'm going to go out today and I just need to know if I need to wear a jacket or not, I'm going to do fine with the numbers on the right? I know how to wield numbers. I know what they signify. I know they signify quantity, amount, right? I don't need to think about the boiling water example and the ice cube, really. That level of representation is a little bit superfluous for me to make the decision about whether to put on my jacket. So, so analog versus digital. That's just a good thing to understand. It's a good dimension to understand about how a representation, where it falls on this spectrum. Now, another interesting thing. There are also non-obvious representations. Some representations aren't based on directly observed stimuli, but are more complex and nuanced about implied relationships. So we're stepping away from even the nice, happy, concrete things that we must force our brains to abstractly represent, and moving into a space of invisible, strange, social things that the brain must be forced to represent. Fun. So, let's talk about birds. Bird dominance hierarchies. Consider a bird observing the world. It runs across a red and green bird who are having a bit of a spat. The red bird comes out on top in this spat, whether that's like physical violence or just snatching the food better or whatever, whatever. There's competition going on at times in these environments, and Bluebird is noticing, oh, Redbird won, okay. But Bluebird continues to observe the world. Oh, I saw Greenbird win against Orangebird. Oh, I saw Orangebird win against Purplebird, and Purplebird win against Yellowbird. Question is, now, can this bird make a prediction about who's going to win in this scenario. Redbird is come into conflict with Yellowbird. Bluebird's going to know pretty quick. Now, these birds have never interacted before, right? Here's the interesting thing, is that this bird should be able to make this prediction, right? You know the answer. Redbird's probably going to win, right? Yellow has only ever lost, and red has only ever won, right? This is a pretty clear one. What about, though, Greenbird versus Purplebird? Greenbird has lost. Greenbird has won. Purplebird has lost. Purplebird has won. Is that a 50-50 shot? So it's more obvious for, if you're just thinking about their track record, that Redbird and Yellowbird, clearly Redbird's won better things, right? That's got a better win rate. But the Greenbird and the Purplebird are a little more confusing, and you should be able to tell the difference, though, because transitive inference is something that you can pick up as this little blue bird. You know that there's something about the fact that there's a chain of win and loss here. Redbird has never lost to anyone below it on this little chain, right? So Greenbird and Purplebird, it would be a smarter call to bet on Greenbird. It's because Purplebird has lost to things that Greenbird has beaten. This is all very fun and toxic, and let's watch these birds fight for dominance, blah, blah, blah. But the idea, though, is that whether or not this is exactly how this all works in the environment, it is something we can absolutely learn, and is kind of useful, especially if you get into more maybe violent species than some birds picking over breadcrumbs, right? If you're gorillas, you might... Not that gorillas are continuously violent, but if they do get violent, things get bad. So violence becomes this more important factor in their environments. So bird hierarchy. Some birds can keep track of this dominance so that they can engage with the environment more safely. So these very abstract relationships based on working out information that is not available in the world. It doesn't exist in the world. It only exists in the sort of statistical and inferential and logical space of, ta-da, the mind. Though the mind is obviously also in the world, right? But the question is, if this is something that we're capable of doing, or birds at least often show proclivities toward, then what are the representations we would need to be able to do these operations, right? What do birds need to be able to keep track of these hierarchies? At minimum, birds need to keep track of things like the identity of individuals in their environment, right? They need to know the difference between redbird and orangebird. That's not trivial. That's actually pretty important. I need to have a unique signifier somewhere in my neural patterns that says, oh, that's redbird. Oh, I hate redbird. Redbird's a jerk, right? And you have to keep track of the past scuffle performance of the environment. So those are the absolute basics, right? You need to sort of a match history and IDs, right? So, but there's also these complex networks, even if we were just storing a table of every bird ID and every, fight outcome, there's still this non-obvious network, right? The relationships between all the birds. The fact that redbird beating orangebird implies something, redbird beating, it's greenbird, right? Yeah, redbird beating greenbird, and then greenbird beating orangebird, and so on. Those connections together are a little bit more, there's something more there, right? It's not just in the list. You need to have a more useful way to capture that. So when it comes down to the question of bluebird finally encounters redbird and they're going to fight over food, what do? You probably leave, right? You probably maybe going to not hedge your bets. Bluebird is untested, Maybe Bluebird decides, maybe I'm the best bird, and they tries to fight. But odds are good, this is a tough bird. What about against Yellowbird? Odds are good. I could get that food before Yellowbird. I bet. Unless maybe I'm the worst bird. It's possible I'm the worst bird. But what it comes down to is you have a good estimate of each one, right? You have this good estimation of how food powerful the redbird is versus how food powerful the yellowbird is. Why? So this comes to the concept of internal models. You predicted which bird you would win in a scuffle against, right? Mental models are these representations that allow us to keep track of these more abstract relationships. It helps us make use of causal structure. Yeah, our old friend, contingency, right? Tree leads to fire. Fire leads to smoke. And so on. There's relationships between all of these. We know that fire can burn tree. Tree can fuel fire. Smoke signifies fire. Fire creates smoke. There's all these little connections between these concepts, these little internal models that give us these relationships that are abstract. You don't necessarily have to see them in the environment. So, given that we can track causal relationships mentally in these internal models, what the most powerful thing is, remember, prediction is key. We can simulate possible outcomes. Our internal model state will likely map onto the way that the states will change in the real world objects. Tree burning leads to smoke. That is something that we don't have to know. We don't have to see visually to be able to kind of know it, to make this prediction, letting us make really useful predictions, right? So here's an environment. Little guy looking up at a tree with an apple in it. My prediction is that if I shake this tree real good, it's going to drop the apple. I can also make the prediction that if I throw something at the tree, it might drop the apple. These are both useful predictions. These are both ways of interacting with the world based on things that are not obvious. These are relationships that we can put together. And we may be able to build them out of nowhere. The concept of ingenuity, right? You don't necessarily have to have shaken a tree to know that an apple could fall if it was shook. You might just know, oh, that apple stem looks a little thin. Maybe I'll give it a jostle, because we might know that jostling things leads to breaking them sometimes. All put, internal models are really key to how we can track complex real-world situations in very lightweight, small, abstract versions of them. Very good stuff. Very important to how we work. One last thought on the ways different representations work is the concept of explicit versus implicit representation. So explicit representations are the ones that are going to refer directly to objects, right? Tree in the world, that's a thing that exists, right? It's inherently meaningful. These are nice because they're very well grounded. We talked about the grounding problem a little bit before. They are inherently meaningful. It's nice and easy because we know that tree means tree. But implicit representations are some of what we've been talking about here. They're the ones that require additional processing to be meaningful, and they are inherently a lot more abstract. Processes. So what is the process of getting the apple down from the tree? Causation. What will happen if I throw a spear at the apple? Right? Relationships. How is this bird stronger than this bird? All kinds of abstractions. Right? So implicit representations are powerful things, and they are more ghostly. They are more difficult to contact. They are up there somewhere, and we are certainly wielding them, but they're harder to pin down. So, writ large, this has been representation. showing how the simple relationship building of conditioning continues to drill upward and inward into the brain, right? We can make lots of different kinds of representations. There are simple representations that can capture complex structures. There's higher fidelity analog representations and more abstract digital ones. There's directly meaningful explicit ones to more nuanced implicit ones. And altogether, we have the concepts of things like cognitive maps, internal models, and associations are all ways to help us make predictions to guide our behavior in the world. And that is why we need to represent things from the outside world internally, because we can start to do a little bit better stuff with a little less effort if we do that. Now, there is a whole world of, we could say, issues with the fallibilities of representations. For example, there's a world of cognitive bias that you and I are all susceptible to, and this is just the beginning of those edges, right? The ways that we abstract the world into our internal representations can be deeply flawed. Just because we don't recognize it doesn't mean it's not a failure, right? For example, a useful and quick representation that's very abstract, tree, throw thing at tree and hurt, knock part of tree down, tear a limb, whatever. It may miss lots of critical elements, leading to bad misconceptions. For example, not realizing that damaging the tree to acquire apples might reduce the tree's apple producing capabilities in the future, leaving you with nothing to eat. That's been made more and more clear on the global stage lately. Just keep this in mind. There's a whole, you could do an entire class on cognitive bias, and one day I might. But just because we can wield an idea doesn't make it right. And just because we can't wield an idea doesn't make it wrong. So, important, broad concepts. Anyway, that's it for this time. As always, final thought. Consider a concept you've realized in your life so far that you were very wrong about. Like, holy crap, wrong. How did you come to understand that concept in the first place? How did you realize you misunderstood it? Carefully consider how the representation of that concept changed once you better understood it. What changed about it? More relationships to other concepts? A more analog representation? More robust internal models? All right, that's it. Thanks. Take care.